A solid feed of 300 kg per hour aluminum hydroxide powder at 25 degrees centigrade and 12 bar pressure and water of 30 kg per hour at the same temperature and pressure are fed in a continuous fluidized bed dryer. So we are mentioning it's a fluidized bed dryer. So our aim is to dry this 30 kg per hour of water that is coming into the fluidized bed. The powder has a pHD between 0 to 10 millimeter with 10 equidistant intervals. It follows GGS distribution function with dispersion parameter 1.5 and maximum diameter of 10 millimeter. So this has been given. The powder pHD has been given. The bed mass, that is the solid bed mass, which is there at the static condition, it is given as 120 kg and it has been fluidized with 4500 kg per hour of air at 1700 degrees centigrade and 12 bar pressure. So huge amount of energy is going through the air. Otherwise it is not possible to dry this 30 kg per hour of water, right? Now use the Geldert classification for sand-like powder. So there are 4 Geldert functions, classification functions, A, B, C, D. We have to find out which Geldert function we have to use for sand-like powder. Minimum fluidization velocity is calculated using Ergan correlation. Use George and Grace TDH model. TDH means the transport disengagement height model, and Tasirin and Geldert elutriation models with all their default parameters. So the parameters they have not given, you can use whatever the Aspen Plus software suggests. The vessel is 7 meter high with solid discharge location at 95% of its height. So if this is the vessel, this is 7 meters. So at this point, it is 0.95 location. So at this point, the solid is being discharged. Its diameter is 0.5 meters. So it is having a constant diameter. So there is no tapered type of vessel. Air is distributed through a perforated plate with 40 orifices and 10 millimeter diameter. Orifice discharge coefficient is 0.8. So they are not giving the pressure drop information, rather they are giving the orifice discharge coefficient so that the pressure drop can be calculated from there. Now what we need to do? We have to analyze the drying process. So we have to analyze the drying process first. That is the first task. And what is the second task? Repeat the exercise with consideration of thermal decomposition of aluminum hydroxide, because this aluminum hydroxide is subjected to a thermal decomposition because air is coming with a temperature of 1700 degrees centigrade. So it is a high temperature. At that temperature, aluminum hydroxide is supposed to decompose into aluminum oxide and water. Okay. And this is guided by power law kinetic expression with K is equal to 1 and E, that is the activation energy, which is 2388.46 calorie per mole. So this is the complete problem that we have to solve. Okay, so let us go back to Aspen Plus and feed in the data. So first go to the properties, because we have to first place the components. So what are the components that we have? We have aluminum hydroxide first. Then aluminum oxide. And they are solids, right? So we have to say they are solids. And then we have water and we have air. So these are the four components that we have. And we will choose solids model. Okay, so property analysis is done. We go to simulation. First, let us specify the particle size distribution and the stream class that we have to specify. So let us go to the setup. So here, stream class, use mix CL PSD. Go to solids, PSD. This is equidistant. Let us see the problem once again. So the powder has PSD between 0 to 10 millimeter with 10 equidistant intervals. So equidistant with 10 intervals. It is 0 to 10. So this is 0 and this is 10 millimeter. Create PSD mesh. Created. Now we go to the solid input. Now let us see what are the inputs. We have 300 kg per hour aluminium hydroxide at 25 degrees centigrade and 12 bar pressure. Water is at 30 kg per hour at the same temperature and pressure. So we will write 25 and 12 bar. So this is 25 degrees centigrade, 12 bar pressure, (30 kg per hour) water. Go to CL solid. Here again 25, 12 bar pressure, and 300 kg per hour aluminium hydroxide. The particle size distribution has to be fixed. Let us see the problem once again. It says it follows GGS distribution with dispersion parameter 1.5 and maximum diameter of 10 millimeter. So the distribution function is GGS. Dispersion parameter 1.5 and maximum diameter is 10 millimeter. Calculate. So the particle size distribution has been calculated based on the information that we have given. So this is the inlet particle size distribution. Okay. Now go to the gas in. We have to give the gas information as well. So in gas, we have the fluidizing air, fluidized with 4,500 kg per hour of air at 1700 degrees centigrade and 12 bar pressure. So 1700, 12 bar, 4,500. So type in over here 1700, 12 bar, $4,500. So the stream input is complete. Now we go to the bed input. Specification, bed inventory. Specify the bed mass. Bed mass is 120 kg. So let us write 120 kg over here. Voidage at minimum fluidization nothing has been told about the voidage of minimum fluidization, so let us keep it at 0.5 only. We can change if we want. We can try out various values, but let us keep for this particular problem. And Gildert classification, next one is Gildert classification, is for sand-like powder. Okay, so let us refer to the help file once again and check which one is ideal for sand-like powder. So this is the Gildert classification. Sand-like particles, group B, that is Gildert B. So we have to use Gildert B function. So choose Gildert B. Minimum fluidization velocity So minimum fluidization velocity is calculated using air-gun correlation. So we use air-gun correlation over here. What else? About transport disengagement height and elutriation model. There they have said that use George and Grace TDH model and Tasirin Gildert elutriation model with all their default parameters. So basically, they are asking us to use the default condition whichever the Aspen Plus has given. So the default condition is over here, you can see it is George and Grace and Tasirin and Gildert elutriation model with all their default parameters. So the default parameters are given over here. So these are the default parameters. We retain them. And for TDH model, this is the default parameter that also we retain. So we do not have to specify anything more over here. Let us go to the operation. It talks about the heat duty, but in the problem we do not have any heat duty information. Already we are giving 1700 degrees centigrade air, so I don't think any more heat is required for drying. And in the problem also there is no heat duty information, so we can skip this information, go to geometry. So this is important. We have some information about the height and the cross section, and that information is so the height is given as 7 meters, 7 meter height, and solid discharge location is 95% of its height, so it should be 0.95 over here. The cross section is circular, otherwise you won't have diameter, right? Diameter means it is a circular cross section. So diameter is 0.5, so you have to give a constant diameter which is 0.5. Okay, so put in this information over there. So this is 7 meter height, solid discharge location 0.95, and text circular with constant diameter to be 0.5. Okay, so that completes the geometry. We go to the gas distributor. Okay, again in the gas distributor we have certain information. First we have to choose a perforated plate. Okay, so it is not bubble cap, it is perforated plate. So if you choose perforated plate, then you have some information that you need to provide. What are those information? Number of orifice. Number of orifice 40. So you have to provide this value 40 over here. Orifice diameter 10 millimeter. So this is 10 millimeter over here. And the discharge coefficient is given, so you have to choose this, and you have to provide 0.8 over here. Okay, so 40, 10 and 0.8. So let us type in these values. So this is 40, this is 10 millimeter, and orifice discharge coefficient 0.8. Okay, so all the information have been given for the first problem, so we just run it. So run the system. Yeah, so results are available. Just go to the stream results. Okay, so here you can see the total mass flow. So this is the solid in, where you have 300 kg per hour of aluminium hydroxide and 30 kg per hour of water. Gas out will have entire 30 kg per hour of water, and the solid out will have no water. So the entire amount of water that is coming through the solid in, that is being dried up due to this high temperature air. That's what it means. So it is successfully drying. And you can check the temperature also. Before checking the temperature, look at this. The gas out will have 9.8823 kg per hour of aluminium hydroxide as well. Only 290.112 kg per hour of aluminium hydroxide is coming out through the solid out. That means this is the amount which is being elutriated due to the gas flow. Okay, and we will expect that this 9.88 kg per hour, that will have finer particles, and heavier particles will go through the solid out. We will check that in particle size distribution. And before that, you can check the temperature of the streams. The temperature of solid is increasing from 25 degrees centigrade to 1544 degrees centigrade. So it's a high temperature, and at that temperature, you do not expect any water to be there. Right? So that's how it is functioning. Now we'll go to the particle size distribution and check it further. For that, you have to go to CL/PSD substream. This is the particle size distribution. Here you will see gas out will have this particle size distribution, and from 0 to 1 millimeter it is 92%. Right? 92% of the solid particles that is being taken away by the gas is between 0 to 1 millimeter. And then 7.5% is 2 millimeter, then 3 millimeter, etc. And anything above 4 millimeter is negligible, because that is the heavier particles. Okay, so that is not going out. Only the finer particles are only taken out by the air due to elutriation. Right? And that is what is expected. Now we go to the second part of the problem. Second part means here we have a thermal decomposition. We have to consider thermal decomposition of aluminium hydroxide as per the following reaction. And this reaction mechanism has to be fed in to the fluidized bed. So it will no longer be a fluidized bed dryer. It will be a dryer because water will be dried, but at the same time it will be a reactor as well. So this reaction has to be entered. So for that, let us enter this reaction. So for that, go to the reaction. New. Now let us see once again what is that. It is a power law kinetic expression. Okay. So this is a power law kinetic expression. New So this is aluminium hydroxide Cl. Let us see what is the equation. This is 2 aluminium hydroxide converts into 1 mole of aluminium oxide and 3 moles of water. So this is 2, or rather minus 2 over here, and 1 exponent. This is aluminium oxide solid, 1 mole, and water, which is 3 moles. Right? And what is the kinetic equation? It is a power law. And reacting phase, entire operation is happening at vapor phase, because at 1700 degrees centigrade, it cannot be a liquid phase reaction. Okay, so do not do this kind of mistake. Quite often people forget to identify the reacting phase properly. So you have to select the vapor phase. K is equal to 1. What else? We have K is equal to 1 and capital E is equal to 2388.46 calorie per mole. So we write over here 1, and this is 2388.46 calorie per mole. So no other information has been given, so we keep the kinetic equation as it is. Now we have to go back to the fluidized bed model, that is B1 block, and we have to add in this reaction. So the available reaction set is R1, which we have just created. So we just select this reaction R1 and we will run the system. Okay, so let us run it. Okay, run is not successful. It says results available with errors. So let us see what are the errors. Check status. The following unit operation block completed with errors. So just press B1. It says M balance or material balance. M balance. Material balance loop did not converge in 50 iterations. Check stoichiometry, molecular weight. So this error is being repeated. So there must be some problem with the convergence in reaction. So let us go back to the reaction in fluidized bed input. In convergence, so here you see the reaction convergence, mass balance convergence solver. Broyden solver is being used. And with 50 iterations, it is not working. So there might be two solutions. One is you increase the error tolerance, which is not advisable. Increase the maximum iterations from 50 to something higher. Or you can use a different solver. Here, Broyden has been used by default, but we can use Newton also. Let us try Newton first. If it doesn't work, then we have to think in some other way. So let us choose Newton and run it once again. That serves the purpose. So now results are available. So we are happy. Let us go back to the results once again. So for that, go to streams. Okay, so now first you see the mass flow rates. Now here you can find the reaction has occurred. You had given 300 kg per hour of aluminium hydroxide through solid in, and solid out, you see how much of aluminium hydroxide left? Almost nothing. And the entire aluminium hydroxide has been converted into aluminium oxide. And some portion has come into water. You can see over here. Earlier it was only 30 kg of water that is being dried up and going to the gas phase outlet. But now we are getting 133 kg. That means 103.923 kg per hour of water that is coming out as a reaction of thermal decomposition of aluminium hydroxide, and that is being taken away by the gas output. Okay, so that is our inference. Now look at the particle size distribution. Here you will find particle size distribution once again. Here you will not get any new information. It is almost the same as before. In the gas outlet, mostly you will find 99.5% of solid particles. They lie between 0 to 1 millimeter. And when the particle size goes beyond 3 millimeter, then the amount in the gas phase is very low. So most of the particles lie between 0 to 1 millimeter, and that is expected because only the lighter particles will be flown away through the gas phase, not the higher size particles. And the particle size distribution in the solid phase outlet, at least for the higher size particles, they are almost same. For the lower size particles, obviously it will be a bit different because most of the lower size particles have been flown away in the gas phase. So there will be a slight difference between the particle size distribution of inlet solid and outlet solid. Okay. With this, we come to the end of this lecture. I hope you have enjoyed it, and we will come back with yet another interesting lecture very soon. Thank you.